everyone. Welcome back to the class of AccentUs for this particular YouTube channel. And today we are doing current electricity part 2 for class 10 ICSE boards. Okay, so we have already completed a few things about the current electricity. We know what is resistance, resistivity, and other parts, and the concepts of EMF, potential, and other things. The nature of current flow and everything we already have done. So today we'll be dealing with the combination of resistance and other interesting aspect of current electricity related to this circuit. Okay. Now today we'll be knowing what electric circuits are, how it works, how cell works, how the resistances are connected, in what way they are connected, and how we can obtain a better network or better electric network. Those things we'll be doing today. Alright, so keep your classwork ready. We'll be starting our topic with the concept of EMF. Okay, here we start. So we have to understand what is the electromotive force or EMF of a cell. Before I discuss this topic, eventually I told you a bit of things about this EMF in the earlier video of current electricity part 1, but let me elaborate that about this particular concept because it is very important. Now you see how we draw current. We draw current from a source, and that source ideally for us, for within our domain, is a cell or a battery. Okay, so it is a DC source which we use. So what we can understand that this cell or battery, what they do is they convert chemical energy into electrical energy. That means we have certain cathode and anode, and there will be some ion exchange, and due to this ion exchange, ultimately the result is that we'll obtain electricity out of this chemical reactions or out of this cell or the battery. Okay, so ideally when a battery or a cell is built or manufactured, then we always calculate what is the amount of material or the substance or the chemicals we are pouring into this particular cell or battery, and with respect to that we can actually calculate that how much energy this particular cell or battery can provide to the external circuit. Okay, so in this process we ultimately can understand that how much electrical energy we can actually convert from this particular thing. Okay, and see, it's basically an energy transfer, and energy is the capacity of doing work. This is the basic definition of energy. And so we can understand that during this ion exchange there is some external agent which is doing some work, and due to this the current chemical energy is converted into electrical energy. So there is some amount of charge which is moving, and there is some amount of energy which is at expense. So we can understand that potential is amount of work done per unit charge to move a per unit charge. So here also during this transfer we develop a certain amount of potential. Okay, so when we actually build the cell or the battery, we always calculate this in through numericals, like the sum we did in chemistry in stoichiometry. So similar way we can calculate and find out that how much potential that particular cell that we have built or manufactured that can provide to an external circuit. We can actually calculate, we can do numericals and find out what is the capacity of that particular cell or battery. Okay, so we'll mark, so we will mark the battery with certain things. Say 10 volt is the marking. Okay, fine. So this measure is called the total capacity of that cell or battery which it can provide to an external circuit. But ideally what happens when the conversion occurs, start occurring, that means the chemical energy is getting converted into electrical energy. During this transfer, during this conversion of energy, there is some certain of loss. Now this loss occurs due to heat, and there are some other technicalities within the cell or the battery which causes this kind of loss which we incur. And due to this, the 10 volt, the cell of the battery which was marked, calculation showed us that it is having a capacity of providing a potential of 10 volt. but practically when we use that in a circuit, due to these losses that it incur within, so finally maybe we are getting a potential of say 9.5 volt. So we can understand that 0.5 volt, this potential is lost. Okay, so this is we are not able to fetch from the cell or the battery we are using, though it is marked as 10 volt. Okay, so I told you situation, okay, and I told you with certain hypothetical values so that you can visualize what is actually happening, and here lies the concept of EMF. Now what it is? So a cell which is built, it is capable of providing a potential of certain value, say 10 volt here that we took as an example. So this 10 volt is the EMF. That means it is the amount of potential a cell is capable to transfer to an electrical circuit when it is not connected to the circuit. That means when we are not actually fetching current from that particular cell, the potential that it can provide to the circuit is called the electromotive force or EMF. Ideally, we won't get that. Okay, practically when we use this in the lab experiments or in the real life, we won't get this EMF as it is. We get lesser than this value. Okay, so this is the concept of EMF, and the potential that we are obtaining within the circuit. Okay, how can we measure it? We can measure it through a voltmeter because it is a potential. So potential what we are obtaining within the circuit, within the arrangement of the circuit, that is called the terminal potential. That means that is the potential effectively. I repeat, that is the potential effectively the cell is transferring towards the external circuit, and that is called the terminal PD. What did I say? Again, this value, this one is known as terminal PD. Okay, so what is the relation? If EMF is this, okay, EMF minus this terminal PD is the loss that we occur within the cell. So this expression is very important. You will come to know why it is so important just after a few discussions. But this is the form. So EMF is the ideal situation that we should get, and terminal potential is the value we actually get when we connect a circuit towards a cell or a battery. Okay, so this is the concept. One is capable of, another is what we obtain, what we retrieve actually, the exact value. There is a loss, I tell you. Whenever any energy conversion occurs, there will be a loss. The simple loss is heat energy. Whenever any chemical reaction occurs, most of the chemical reaction are exothermic and they will liberate heat. Even for the batteries, you will see after a certain amount of use, it gets heated up. So there will be a loss, and the term EMF will be greater than the terminal potential. Alright, now let us go to the next topic. Let us do a problem. Okay, this is the first problem of today's class. But we say that we have a cell of 3 volt and it is having an internal resistance that we don't know. So what I say is that we have a variable resistor here. You can see RH, and when we are changing the resistance, these values are changing obviously. So 1.5, when the ammeter reads 1.5 ampere, it says that across the variable resistance, the potential drop is 2.7 volt. Okay, so this is the information given, and they have asked us to find out the internal resistance of this particular cell. Eventually, we also don't know about the external one. Okay, so you cannot use that formula small r equals to that thing E by V minus 1 into capital R. We are not able to use that formula because we don't know the capital R, it is variable. So, but the rest of the informations are there. So obviously, we can easily use one thing, that is E minus V is small I into R. We know I, we know V, we know E. So eventually 3 minus 2.7 is 1.5 into R, and from here you can easily understand that this is 0.3 divided by 1.5, and what will be the answer? It is 3 by 15, so 1 by 5, so 0.2 ohm will be the answer. Okay, so it's simple. I told you, EMF, internal resistance, these are very interesting and easy concepts. Okay, so you have understood this. Alright, now let us move into the next topic. So now we'll be doing a concept called internal resistance. You know already that the EMF marked in the cell and the potential obtained within the circuit, they are different. Obviously they are different, always we find it that way. So we have to somehow account this difference. Okay, there is some amount of potential of the energy is lost, and this energy is lost within this battery or the cell or during the conversion of chemical energy into electrical energy during that time only. Alright, so here we have to understand that the potential which we are obtaining for this external resistance capital R, which is recorded in the voltmeter, which is always connected in parallel to the equipment, and also the current which is flowing through the circuit we can calculate in the ammeter, which is connected in series in the circuit. And we have the cell which is having an EMF E, and already suppose we are thinking that there is some amount of lost volt. Now what is the lost volt? The lost volt is basically this, the total marked minus total obtained, and that is the amount of loss that we are incurring. Okay, so this is the thing, and then we thought, okay fine, since there is a loss and we cannot actually account for it, so we thought that within the cell or within the battery itself there is a resistance which is actually consuming this amount of potential which is lost. Okay, and after this loss only we are getting the current or we are getting the potential within the circuit. So within the battery, within the cell, this internal resistance is creating or causing this loss to occur. So we can say that E minus V is small I into small r, which is termed as internal resistance. Okay, so this is now we have an expression. Now what we can do is very simple, that we can divide the whole thing into this form, that is by capital V, and you know that capital V is equal to basically I into capital R, because this is the potential drop across this resistance. It is connected in parallel across this resistance. So potential that what we are obtaining in the circuit is V, and that is equal to small I into capital R. Okay, so from here we can easily calculate the value of small r, which is capital R into E V minus 1. You see, we have a simplified expression in order to calculate the internal resistance of this particular circuit, or this particular cell using this circuit, and we have this expression small r equals to capital R into E by V minus 1, and this E is the EMF marked in the cell and V is the potential retrieved within the connected circuit. Alright, do it. Remember this expression. This is very important. It will be used a lot of times, even in the latter part of current electricity. You will see that this part is used lot during doing the numericals and other things. Okay, so hope this you have understood, that we have understood the concept of internal resistance, we have understood the concept of EMF properly. Now that we have understood why this loss occurs and how we can account for this loss, and that is the reason why we have brought this concept in current electricity called internal resistance. So now we are going to learn a very interesting topic for current electricity, which is the combination of resistances. You see, we don't use a single resistance or at the real practice. We use a lot of resistances together, and that's the reason why we should know that what is the effect of combining a lot of different resistance together and what does it give us. And for that reason, we'll be knowing this thing, the combination of resistance, and also you should know that there are two different types of combination. One is called series combination, that is Series means one after another. The way you visualize series combination is that one resistance will be followed by another, will be followed by another, and so on and so forth. So let us draw such arrangement. You know the resistances are like this. So let us take three resistances R1, R2 and R3, and we are passing current through it. And individual resistances, they will develop individual potential drops, because for each of these three different resistances we have different potential drops occurring at individual resistances. But remember one thing, that current remains constant here. Current remain constant. Okay, this is the main logic behind series resistance, and that is that the current will remain constant. So total potential, if it is total is V, then we can say that these are the sum of all these three different potential drops. And so V is equal to I into R equivalent, that is the equivalent resistance I am going to obtain out of all these three resistances we are using here. And I V1 will be equals to I R1, this is I R2, and this is I R3. So effectively we are getting an expression which is like this. So equivalent resistance in series combination is the sum of all the resistances thus connected, and it is just R1, R2, R3 addition. So you can understand, in series combination the effective resistance of the circuit increases, so effective current gets decreased. Okay, so this is one type of combination that we have for the combination of resistance. Next we are going to go for the parallel combination. Before going to parallel, I must again repeat certain things. In series combination, remember one thing, that the current remain constant throughout all these resistances. The same current will flow. Okay, and the second part is that the individual resistance will occur the individual potential drops. Added them, you will get the total potential of the given circuit, that is V equals to sum of all these three potentials. Okay, now I hope you have understood. Now let us move into the parallel combination of resistance, which is more interesting. Okay, now let us go for the parallel combination. We are going to do this right now. Okay, please do copy these diagrams and all these circuit diagrams in your classwork, so that for the future reference you can have this in your classwork, so that you can revise it very easily. Okay, so we have taken three resistances in parallel. Parallel means there will be a single branch, and then the resistances will be connected, and then the branch will be closed, and it will go towards the main circuit or the source supply, whatever. So let us take, this is R1, this is R2, and this is R3. If the main current coming to this circuit is I, then what happens here, the current is actually, it gets divided into three parts, and finally it again combines up to get the main current I. And even another point is that suppose if these two are the junctions A and B, where the resistances are diverged, then the potential between A and B will remain constant. So VAB is constant. Unlike the current was constant, here current is getting divided, and potential was here, it was individually different. Now here all these resistances will have the same potential. Okay, so what I can write here, that I is equal to the main current is sum of all these three currents according to the law of conservation of energy. Current is a form of energy, so whatever current it was coming to the junction, the same current will get divided into the three parts towards individual three resistances. Okay, so I is equal to I1 plus I2 plus I3, and I is equal to, you can say the potential is constant VAB, you can write VAB by R equivalent, and that is equal to VAB by R1, and that is equal to VAB by R2, and I3 is equal to VAB by R3. So effectively I am obtaining an expression for the parallel combination of resistances, which is equal to 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. And here, interestingly, that in parallel combination the resistance was getting magnified, but in this case the effective resistance is lesser than the least resistance connected. Please write down this particular line. I am repeating, let the in parallel combination of resistance, in parallel combination of resistance, the effective resistance is lesser than the least resistance connected in the circuit. Okay, so it is the least resistance effectively in parallel combination. You can understand, unlike series combination, the effective resistance decreases, so the effective current towards the circuit it increases, and the same potential is applied towards each of all these resistances, which is equal to VAB here. You can see in this particular diagram. So you can understand, in household circuit we prefer to use parallel because all the appliances is manufactured at a particular standard potential that that we use in excuse me, in domestic circuit, which is 220 volt. For in our country it is 220 volt 50 hertz AC, but still in AC also the potential will remain constant in parallel combination, and we use in household circuit we always connect everything with respect to the parallel combination. Okay, series combination has also got a lot of things. We'll come to know about all this later on. Right now, so this is all it. The series combination and parallel combination is done here, and now we'll move into the next topic. So now we know what is series and what is parallel combination, what are the rules for it. I repeat again, for series combination current remains constant, and for parallel combination the potential drop across the resistances, they remain constant. Okay, so we have an A here, a network containing resistance which shows like, it looks like A. Alright, so here is, and they have asked us to find out the equivalent resistance between X and Y. This value of resistance we have to calculate. Okay, no issue. So first let us understand how we can visualize, how we can see to the circuit. Okay, what you can see here, before we come back to X and Y, we have other junction P and Q. So let us first resolve this section. Okay, so P to Q. Now what is this? If I want to go to P to Q, we have two pairs. One is PRQ, one is PQ. So PRQ is 3 ohm and 3 ohm. So resistance across PRQ is 3 plus 3 because it is series, and resistance along PQ is 3 ohm, and you can understand they are in parallel. Okay, so I can write 1 by RPQ is equal to 1 by 3 plus 1 by 6, and from here you can easily write the resistance between this arm. Now these all resistances will collapse to PQ. There will be nothing else. So RPQ is 2 ohm. Okay, great. So now if I go from X to Y, I have a path X, P, Q, Y. What I'm saying, X, P, Q, Y. So all these resistances, they are following my path. There is no branch. This is a single path. So we can understand they all are in series. So I can write the effective answer. The effective equivalent resistance between X and Y will be summation of these three. Now this is 2 ohm now because all this has collapsed to 2 ohm. So it will be 3 plus 3 plus 2. Okay, so 8 ohm will be the final answer. You see, if you can visualize, you can identify where we have series, where we have parallel. When you are going through the circuit and there is no branch, that means it is series. You are going through a circuit and there is a branch. Branch means when you have alternate pairs. Okay, that is we call the branch. That is parallel. Parallel means we have 2, 3, 4 paths for current to divide and go through the network. But series means the same current will flow throughout, so there will be no branches, there will be no division of the path. Okay, so this is it. Hope you have understood. Now let us go to the next topic. Okay, let us do 2 more sums based on the circuit things that we have already learned till now. Okay, we have the first this problem here, which says that we have 3 ammeters A, B, and C. We have 3 ammeters. And they are connected like this. We have 2 resistances in parallel, 6 ohm and 3 ohm. Hope you can understand this is a parallel combination. And we have a cell, nothing is given, and we have a 2 ohm resistor. What is given here, only thing that is given here is the reading in ammeter B, that is 0.5 ampere. Okay, that is only given, and they have asked us to find the values or the reading in ammeter A and ammeter C, as well as the EMF of the cell. They haven't mentioned anything about the internal resistance or any loss that is occurring in the cell, so we are not assuming that any internal resistance of the cell as of now. In the sum they didn't mention. They have asked us to find out the value of the readings in ammeter A and ammeter C and the EMF of the cell. This is the sum. Okay, please write down in your class book and let us now solve it. Okay, so we have this thing, we have one information, the reading of the ammeter B is 0.5 ampere. So we can find out the potential here. Because if this is the reading, this is the potential, I into R will give me the potential, and once I get the potential here, the similar potential lies here too. Okay, so I can get the block, the potential of this block. Okay, and that is very important. Okay, with that there is an ammeter here, and with that there is a 2 ohm resistor, and they have said that their ammeters do not have any resistance. Okay, so we can go like this. The first one, okay, we asked for the reading in ammeter A and ammeter C. You see, I can say that if this current is I1 and if this current is I2 and this current is I, then I is equal to I1 plus I2 according to the rules for parallel combinations. Okay, so I can say I1 I know 0.5 into 6 I1 R1. This potential drop is equal to this potential drop, and that is I2 R2, that is 3. So I can easily fetch the reading of CI2. Okay, this is the reading of C, and that is equal to, you can see here, it is 1 ampere. So this is the first answer we have already got, and the reading of A is I. So reading of A is I. So what it will be? The reading of A is 1 plus 0.5. These two will give me this value. Clear? So 1.5 ampere. This is the reading of A. So these values we have got. Okay. So fine enough. So this 1.5 ampere is the current that we are drawing from the cell. You can understand that. And they have also asked us to find out the EMF of the cell. Now, what is it? We have a 2 ohm here, and we have a block of parallel resistances 6 ohm and 3 ohm there. So there are two blocks, 2 ohm and this block, they are in series. Okay. So let us first identify and calculate the equivalent resistance. Because we know the current, equivalent resistance, once we know, we can calculate the EMF of the cell. This is the thought process. We can calculate the total effective resistance. The total effective current drawn from the cell is known. So this product will give me the potential of the cell. Very good. So let us do this. Okay. So 6 and 3 parallel. So let me say if it is R dash. So 1 plus 3, 1 by 6, and that is hopefully you can understand. Okay. It is giving me that R dash is 2 ohm. Okay. And there is another 2 ohm here. So total resistance is 2 plus 2, they are in series. So the EMF of the cell is I into R, and that is 1.5 into 4, which is 6 volt. So we have got the answers. We have got the readings in ammeter C as well as in ammeter A. Ammeter C is having a reading of 1 ampere. And that is having a reading of 1.5 ampere, and eventually we have also calculated the potential of the the EMF of the cell. Assuming there is no internal resistance, then EMF and terminal potential will be similar. So this is 6 volt. Now let us concentrate another interesting problem here, what we have drawn already. This is also having a block of parallel as series combination. Anyways, here we have a cell having EMF 2 volt. Internal resistance is 3 ohm mentioned. We have 2 ohm and R which is in parallel, they are parallel, and with that there is a 4 ohm. Okay, and 0.25 ampere is the current drawn from the cell. These are the informations given. We have 2 ohm and R in parallel. With that, we have a 4 ohm in series, and we have a cell having an EMF 2 volt and internal resistance 3 ohm. Okay, and the main drawn current is 0.25 ampere. What we have to calculate? We have to calculate the PD at 4 ohm, which is pretty easy. PD at 4 ohm. What is the current at 4 ohm? Is 0.25 ampere. So potential at 4 ohm, resistance will be 0.25 into 4, that is 1 volt. There is nothing else to think even about it. Now what is, they have asked the value of R. Now here we have a lot of things to understand. The first thing is, you see 0.25 ampere is the main current. Okay, good. So if I assume total resistance parallel is R dash, then what is R dash? R dash is 1 by 2 plus 1 by R, and that you can say that R dash is equal to 2R by R plus 2. Keep it, no issue. So this R dash 4 and 3, they are in series. So total resistance is 4 plus 3 plus 2R by R plus 2. Alright, great, good. What is the okay, let us simplify, because unnecessary we will be having other difficulties. 7 plus 2R by R plus 2. Okay. So this is the resistance of the total circuit. What is the current? 0.25 ampere. So eventually this current and this resistance, when they are multiplied, V equals to IR, Ohm's law. So I into R will give me 2 volt. There is no other option. This is the only source here. So I can say 2 equals to 0.25 into 7 plus 2R by R plus 2. You can easily solve this. I don't think it will be a big trouble. I am not going to solve this anymore, because this is quite, you have to just calculate the value of R from this. You can divide it, you can subtract 7, and then you can cross multiply and find the value of R. It's a single variable equation. I don't think it will be a problem for you in class 10. Alright, so do calculate and tell me the answer in our WhatsApp AccentUs group. Okay, so these are the 2 problems that we did based on the series parallel, all these EMF concepts and everything. Okay, hope you have understood. We'll be doing a lot of other problems from the exercise as well. You'll be doing that and send me your doubts later on in WhatsApp group of us. Okay, now let us move into the next topic. Electrical power, and that is the only way we can actually convert electric energy into other form of energy. And we always try to measure the amount of consumption in the terminology of power. Okay, so this is very important. Let us do that. Now electric power is actually fetched from the concept of work per energy only, that we already know about work per energy. So whatever power we define there, it is the same thing which is there in electricity, only the work done or energy is current, electrical energy. There in work per energy we did a lot of things about mechanical energy. Now it is related only to electrical energy. So let's do find out the expression of power. So power is basically work done by time, that we know, right? So work done by time, and work is potential into charge, because definition of potential was work done by amount of charge. So W by Q was V, so VQ is W. Okay, so now what I can see, Q by T is current, that I know. So power here is equal to potential into current. So the unit of power is watt, and in electrical power, and we can say that 1 watt is actually equals to 1 volt into 1 ampere, and this is what we have a basic relationship, but this relationship can be modified. Now how we can modify? First of all, V is equal to IR, that we know from Ohm's law. So power can be also written as I square R, which is mostly used in doing numericals for series combination of resistances that I'll do. These things we use this kind of expression. And also I is equal to V by R, so power can also be written as V square by R. So this is another expression which is also important for doing the sums based on parallel circuit. We use this form. Okay, so series we use this form and parallel we use this form. I'm coming to these things. I'll be deriving all this. But right now, just for the sake of information, you remember. So we have already understood what power is, how we can fetch the the simple expression of power. We have a lot of things to do that will come. But right now, it is the fact that power is work done, electrical work done per unit time, and electrical work done is potential into charge, and that way we can actually get power or 1 watt in electrical terminology. 1 watt is equal to 1 volt into 1 ampere. We definitely have higher units like megawatt, kilowatt. These things are used widely. You find any electrical appliances, you buy anything, even a bulb, you'll see there is something written, and say 10 watt, 11 watt, 20 watt, 30 watt, something is written, and that is the amount of consumption of current electricity that we are doing, and that is the amount of current electrical energy we are actually consuming. That gives us the expression of consumption of electrical energy. Okay, so let us move into the next topic. Hope you have understood this, the electrical power, the basic of electrical power that we have derived here. And now we'll move into the next topic. So now we know power, so let us do two problems so that we can understand power more easily. Okay, don't think it's a huge thing, it's just simple thing. We have simple formula to use and that's it. So we have a problem. There is a geyser of having a rating of 1500 watt to 50 volt. It is given 1500 watt to 50 volt. So they have asked us to find the amount of current the geyser is drawing and the total energy consumed in 50 hours of use. I mean, if the geyser is total use is 50 hours, then what is the total energy consumed? So current we have to find out. So the power is equal to volt into ampere. So it is 250 volt, it is connected to 250 volt, assuming that, because since they mentioned anything. So 250 into I, and from here we can calculate 1500 by 250, which is basically 6. So 6 ampere is the current. So geyser can use a huge amount of current of 6 ampere. Geyser, air conditioner, refrigerator, they take a huge amount of current from the circuit. Anyways, so next is the energy. Energy is power into time. Now power is 1500 watt and time is 50 hours. So 50 hours we have to convert it to seconds. So 50 into 3600 and probably 15 into 5 and then 36. 50 hours, 1500 watt it is. So 75 into 36 into 1, 2, 3, 4, 5, 10 to the power 5. This is the amount of energy they are using. Anyways, but since they have asked us to do energy, this is the value of joule you can calculate, but better is, let me tell you, in ICSE, what you do is, you have 50 hour, right? You express it in kilowatt hour. So 1500 divided by 1000 will give you kilowatt, and R is as it is. So this is 1.5 into 50. So 1.5 into 50 is 75 kilowatt hour. So this will be the answer. This can be also an answer, but that is actually involving a lot of calculation. But in ICSE we have this thing that we can express the energy in kilowatt hour as well. Okay. So anyways, so this is what we have here in this particular situation. And now we'll move into another thing, that is another problem. We have two resistances A and B having 4 ohm and 6 ohm, as you can see here. and they are connected in parallel with a 6 volt power supply. So they've asked what is the power supplied by the cell and what is the individual power dissipation in these two resistances. These are the two questions they have asked. So eventually we have to know what is the current, and for that we have to find the effective resistance. Effective resistance is, you can know, 6 into 4 divided by 6 plus 4. If you just do 1 by R1 plus 1 by R2 in the reciprocal form for two resistances, this is the expression we usually get. So which is 2.4 volt, ohm. Okay, so 6 volt. So what is the current? V by R, 6 divided by 2.4. This is the current, 6 volt is the thing. Anyways, what it will be, if I cancel it, 3 by 1.2, so from here we can actually calculate, that is 2.5 ampere. Okay, so that's approximately, that's a value here. 2.5 ampere is the current. Power supplied by the cell, power is volt into ampere, 6 volt into 2.5. okay, volt into ampere. So 6 volt into 2.5 will give me 15 watt. So this is the answer for the first part. And the second part, eventually you know that it is having a 6 volt, it is also having a 6 volt, and for the power for this kind of parallel combination, I told you about V square by R, you remember? That's it. So we can say power of A is V square by R. And what is VA square? Is 36, 6 square, okay? And then RA is 4, so it is 9 watt. And obviously the next power is again VB square by RB, which is 36 by 6, which is 6 watt. So this is the answers for the rest two part. Okay, you see, so simple. If you just remember where to use which formula, then it's fine. I told you. In parallel combination, use V square by R, and series combination, use I square R, and generally approach V into I. Okay, so this is the thing. All right. I just have to show a small thing about power that will come, and then I'll conclude this particular lesson video. Okay, let's check it out. You see, power rating is nothing very difficult. Every appliance, each and every appliance, they have a power rating. Like we write 300 volt, 300 watt, 220 volt, 250 volt. These are power rating, but this gives us a lot of information. What information it gives? Suppose we have 500 watt, 250 volt. Eventually, you can easily calculate the current, which is power by potential. So you know it will consume 2 ampere of current. You can calculate resistance. How? Okay, so these are the information that we get fed from a power rating. But more important is the how we industrially, industrial way, or whenever we are consuming electricity at our home, how we pay for them, and that is called the power consumption, and that is energy, the energy in industrial unit, and how it is. We call it kilowatt hour. What is kilowatt hour? It is the total amount of power consumed for in kilowatt for a duration of 1 hour. So what we can say that the power, okay, is work by time. Okay, fine. So when we want to calculate energy, is power into time, and kilowatt hour and everything. So if I say 1 kilowatt hour, that means what is that? 1000 watt into R, which is 3600. If I calculate it in joule, so it is equal to 3.6 into 10 to the power 1, 2, 3, 4, 5, 6. So 1 kilowatt hour is 3.6 into 10 to the power 6 joule, and this is the standard amount of energy we consume when we consume 1 kilowatt hour. And I must tell you, in our electricity bill, the 1 unit that they charge is actually 1 kilowatt hour. So 1 kilowatt hour, we are consuming this much amount of energy, which is not less. 3.6 into 10 to the power 6 joule of energy we are consuming when we are consuming 1 unit or 1 kilowatt hour of electricity or energy. Okay, so this is it. I told you that this is a commercial unit of power, and if you have understood what is the concept of power, I did some also, and now I am winding up this particular lesson. Alright, so this is current electricity. We have finished this. Now it's your part. You will sit back with your textbook, with your classwork, notes that you have written today, and also you'll solve examples you'll do, and then you'll do the exercise. I'll send you the homeworks in our WhatsApp AccentUs group. Okay, sure. So till then, bye bye, stay safe and stay productive.